Hello all, welcome to part 2 of the Exploit Research Mega Primer. In this video, we will look at a buffer overflow attack using Memcpy. So without further ado, let's start the demo. I have a Windows XP machine, which is where my victim software will be running, and I have a backtrack machine. This is what is going to be the hacker machine. And I've logged into this backtrack machine using putty, so that probably I can get a little bit more screen space without having to have a full-blown UI. So now what we will do is, the first program which we will look at is a simple program which I have created for this demonstration only. Let me show you how that program looks like. So this is a simple server which is listening on port number 10,000, and what it does is, whenever it receives any data from the client, it goes ahead and calls a function called vulnerable function with that data which the client has sent it, which is stored in receive buffer. And this calls the function vulnerable function, where we have a buffer of size 256. And we use a Memcpy to copy the user input which we received over the network into this buffer, but we copy 1024 bytes. Now, as one can imagine, this server is bound to crash. But that's not the point. We'll take this very simple example to begin with and start our journey into exploit research. Right, so this is the server. Once I double click it, it's going to go ahead and bind to port 10,000 and wait for user input. And I can know the IP address of this remote machine by running ipconfig. It's 192.168.1.100. Now let's focus on first triggering the crash. So let's go back here to the backtrack machine and let's write a very simple script called exploit.py, which is going to be a Python script, where we will connect to this remote service running on 1.100, the Windows machine, and send it some data. So because we have to connect over the network, we'll have to import the socket module and the sys module to get command line arguments. So let's create the socket very quickly. We mention the address family and the kind of socket, which is going to be a stream socket because we're going to connect over TCP. Then we connect to the remote machine using sock.connect, and we pass in the IP address, which is going to be passed over command line, and the port number, which we know to be 10,000. Now we have to send some data, where let's say we're going to send a long string consisting of only A's and 2,000 of them. Now we quickly write sock.send to send this data, which is stored in buffer, and we can close the socket thereafter. Right, pretty simple program. Let me change the permissions to make this executable, and now I can execute it. The remote IP address of the machine is 1.100. So this is where our victim is running. So let me run this. And looks like the data was sent. If we go to the victim, you will notice that we actually get a familiar error message from Microsoft saying this program has encountered a problem and needs to close. Now, one of the quick things we can do is click on here to look at the report. And one very simple indication is the offset. This is where actually the EIP register points to when the crash happened. Contains all 41s. Now, 41 is actually the ASCII value of capital A. You could verify this by doing a man ASCII, and if you notice, the hex value of the character capital A is 41. So what that means is, well, we were able to override the buffer and override the return address. So having said this, now we need to do a little bit of more detailed analysis of this current problem. Now for this, what we will do is we will use a debugger which will give us more visibility. So we'll use the Immunity debugger, which you can download from their website. Now in Immunity, as soon as it opens, on the right hand side you have the register window. This is where all the CPU registers are going to be shown. This is the stack window where you can actually see the stack. This is basically the data dump where you can see various memory locations. And this is where the actual code will be displayed, which we are currently executing. So let's open up our file in this debugger and let's run the program by clicking on the play button. Now you notice we have our code here, the registers, the stack, and then the address dump. So the program is up and running. Now let's go back to our attacker machine and send data. Let's go back, and we actually notice that access violation when executing 41, 41, 41, 41. Right? So there is an error condition, and this actually goes ahead and confirms that the EIP register is getting overwritten with all 41s. And ESP, which is pointing to top of the stack, which is actually shown here, the same memory location, also goes ahead and contains these 41s or capital A's. Now let's look at how we can analyze this a bit more. So let's go back to our slides and understand this scenario. Now this is how our stack would probably look like if you remember the buffer overflow primer for Linux. You have the local variables, the value of EBP, the return address, and the arguments. Now this is the local variable, let's say buffer, which we are currently overwriting, and we overwrite up the stack from low memory address to high memory address, and this overwrites all these values effectively, and this is how currently the stack is looking like. So this return value needs to be popped into the EIP register as soon as this function returns, and now EIP contains the 444444, which is actually an invalid code address to execute. Also importantly, as we found, that ESP is pointing basically to a section which also contains a lot of this character, the A characters, which we have currently displaced. So this is where we are currently. So now what you noticed is we've overwritten the entire stack. So let's look at how we can analyze this better. So what do we require for a successful exploitation? Well, very simply, instead of just overwriting this with random digits, numbers, or characters, what we really want is to craft this overwriting in a very tactful way. And the whole idea is to overwrite the return address with an address which points back to the stack, right? And at this location where this address is pointing back to the stack, we have our payload, which is the malicious code we would like to run. So as an example, let's say ESP, after returning from the function, is actually pointing to AABBCC08. Now what we can do as an example would be to overwrite the return address with the value AABBCC08. So now when the function returns, this value is now put into EIP, and EIP is now pointing into the stack, and at this location the next instruction will be executed. Now here is where our payload is, and hence our payload gets executed. So this is how we can plan for a successful exploitation. But there are a couple of things we need to figure out before we can do this. So the first thing is, well, right now we've just overwritten it with AAAA. How do we know the exact offset of the return address in this stream of capital A's? Also, how do we know exactly what address to place here, which could be, let's say, the top of the stack after the function returns, or the value of ESP? So basically what we need is two things. First, we need to figure out where is ESP pointing after the function returns, and second, what is the offset within our stream of capital A's which is overwriting the return address. So how would we go about finding this? Well, for this we are going to leverage a little bit of help from Metasploit. So we are in the Pentest Exploits Framework 3 Tools directory, and here we go ahead and run pattern_create, which is a little program which can go ahead and create a pattern of characters which we can use to figure out the offset. So let's say we request it to generate 2000 characters. Now if you look at the pattern, capital A small a 0, capital A small a 1, capital A small a 2, capital A small a 3, etc. So this is actually a pattern which is being created. Now what we want to do is send this entire string and have the buffer overwritten, and then figure out exactly at what position is the return address being overwritten and at what position are we filling up the top of the stack, or what is ESP pointing to, right? So let's go ahead, copy this, let's go back to this terminal, and what we can actually do is basically just copy this entire thing in, and on the victim side, let's go ahead and run the program once again. Program is up and running. Now let's launch the exploit. If we go back here, the program has crashed, but at this time we actually see the values are different as expected. Instead of all 41s, now we have 6A, 41, 39, 69. And ESP, which is the top of the stack, is pointing to the location 0022FB70, which contains the ASCII value 0A, J, 1, A, and so on and so forth, which is basically hex representation of 31, 6A, 41, 30, right? And what we need to find out now is, in this pattern, where exactly is the return address being overwritten. Now, in order to do this, we basically will employ a companion program called pattern_offset in the same directory, and what we have to give it is the pattern which got copied into EIP. So in this case, it's the hex value of these characters which we see, which can also be input to pattern_offset, and this is 6A, 41, 39, 69. So we have 6A, 41, 39, 69, and pattern offset tells us that this is basically located after the 268 character in this pattern. So after, let's say, 268 characters, the next 4 characters or the next 4 bytes is what is overwriting the return address, which in turn is getting copied into the EIP. Similarly, let's look at where ESP is getting overwritten. Well, the value contained in the place where ESP is pointing to is 0A, J1, capital A. This is at 272, right? Which is very interesting because it is just the next 4 bytes after the return address, as expected in the most common case. So if we kind of look at the stack dump, this is ESP 0022FB70, and just 4 bytes before that is the return address, which is 6A, 41, 39, 69. So basically we want to overwrite this return address, which is going to be put into EIP, with the value of ESP, so that this address actually points to this location, and from this location onwards, moving kind of higher up in memory, what we are going to do is put our payload. So if we refer back to the presentation, this is basically just in an inverted way, because in this case this is high memory and this is low memory, right? So we can invert this whole thing. This is our return address, and above that is basically where we are going to store our payload. So idea is, if you notice, the stack is located at 0022FB70. We have to store this value inside the return address so that this is copied into EIP, and then EIP is going to point back into the stack, which is the next 4 bytes, and then from there on execution will start, which means our payload will have to be positioned from ESP onwards towards high memory. Right? So this is going to be the game plan. Now let's go ahead and do this. So before we actually start writing the whole payload and all of that, let's quickly first verify that our conclusion is actually correct. So basically what pattern underscore offset is telling us is after the first 268 bytes you have the return address. So let's actually fill up the first 268 bytes with just A's, as in the previous case, as in the first case. Then let's append 4 B's after that, and after that basically is ESP. So let's go ahead and append C's after that for 4 more, and let's again go ahead and append just capital A's post that, let's say 1900. Now if our assumption is correct, then what should actually happen is basically till here are the first 268 bytes, then we have the 4 bytes of the return address, and then we have basically what ESP is currently pointing to, and then is where we go ahead and position the payload. So to quickly write up what we would assume, this B will overwrite EIP, which is actually nothing but the return address, and this C will overwrite the top of the stack, which is ESP. Now let's go ahead and run this code. Before that, let's quickly just restart our wonderful machine. Let's run the server. Again, there's been a crash, but here is something interesting. EIP now contains all the values 42, 42, 42, 42, which is nothing but the hex representation of capital B. So if you go back to our program, this is exactly what our assumption was. Our hypothesis was that capital B is going to overwrite EIP, which is what has happened, and capital C, first 4, is going to be overwriting the first 4 bytes pointed to by ESP. And this is exactly what is happening here. So if you notice, first 4 bytes has been overwritten by all C's, and after that you again have A's. And as expected, all B's have overwritten the return address, and basically below that in memory is once again you have your 268 A's, right, as expected, which is starting from here. So now let's see how we can exploit this. Basically what we said was that the return address has to point to ESP, which is the top of the stack. Now we determined in a previous experiment that the value of this is ESP was actually pointing to 0022FB70, which is basically just the value which we looked at this point. We can even verify that by running the program, which is currently running, and going ahead and exploiting it once more. Let's kind of quit without saving, and basically ESP is 0022FB70. Let's go back to our program here, and what we are going to do is we are going to overwrite the return address with this value. Now because of the little Indianness, we would have to write this in reverse order, right? What that means is, well, 0022FB70 has to be written in reverse order as 70 FB 22 and 00. Now notice the /x is basically an escape sequence which is telling Python that to interpret this as a single hex value for a byte, right? Okay, so we have 0022 FB70 written in reverse order, and now this is where ESP will be overwritten with the payload. So where is our payload? Well, in one of the previous examples in the buffer overflow for Linux, I showed you how to write and create your own payloads, right? But as you notice, it's not very scalable simply because there is a lot of stuff one needs to do in order to create a payload and optimize it. This is where Metasploit comes to our rescue once again. We'll use this tool called MSF payload and run it, and this will give us a lot of input about the different payloads which are available and how we can use them. It takes a little bit of time simply because it loads all the modules and probably dumps them. Now we'll discuss about staged payloads and all of that later. For this example, we'll take up the simplest payload, which is binding a remote shell to a port. Now many of you who may have used Metasploit, you would have noticed that, well, once you break in, you spawn a shell and connect to it. Basically, this is what is called a remote shell, and in typical cases, remote root shell when you have root privileges because of the exploitation. So we will use this. Now, in order to use this, let's again run MSF payload, give it the payload we are interested in, and the S command will give us a summary of what are the inputs expected by this payload. Okay, so the inputs are the exit function, which by default is process. We needn't worry about it at this point. Then the local port or the listening port, which is all fours, which is okay. And the R host, well, there's no need to give it. And if you don't give the R host by default, it will just go ahead and bind to all available addresses on the remote host. So I think the default options are good enough, and hence you do not need to tamper anything here. So now we will go ahead and tell MSF payload to generate the payload in C array format. So let's go ahead and wait for it to give us the shellcode. Awesome. Let's copy this up, go back to our code and copy this here. So now what is going to happen? Well, we are going to override the return address with the top of the stack, and the top of the stack currently is actually pointing to a location containing this shellcode. Hence, in effect, EIP will go ahead and point to this shellcode and execute it. Right, so let's try this out. Let's restart the process remotely once again. And let's go ahead and run our exploit. Run it. Now, note something very interesting. This time there is no crash yet. The program seems to be still running. This is a very good indication that our payload has succeeded. Now, a remote shell should have been connected on port number 4444 on the remote system. Let's verify this. Let's use NC 192.100. NC is netcat. Hopefully all of you know that. Voila! We have a shell. So if you notice, the program is still running stably while we have a remote shell on the system. We can verify by doing an ipconfig, and it tells us that actually we are on the remote system. So now we are running with the same privileges as this process, and if the process was started as root or the administrator user, as far as Windows is concerned, we would have admin privileges. Right, so once you have a shell, well, you can go ahead and do a lot of interesting things. We'll come to that later, or maybe you've already seen the Metasploit Mega Primer about what you can do. To verify that everything is working fine, even without running it in the debugger, let's run the program in a standalone way. Okay, so I'm kind of having to record this in breaks because of some weird reason. My audio driver seems to be crashing off and on. So, okay, now to validate this properly, what we can actually do is go down to the actual directory and run the program independently. Then go back to our exploit terminal and send the exploit code. So now you would notice that the program is still running. Our exploit code is sent, and now we can go ahead and connect to this remote port which would have been created, which is 4444. And as expected, we are getting a remote shell. So we can actually echo something like hack you into a file, let's say h.txt. This file would have been created remotely, and then we can even type in notepad h.txt. What you would notice is that immediately it's not launched, something to do with the way desktops and all of that kind of work on Windows. But the moment you kind of exit this, you would notice that Notepad gets launched, and basically with the phrase hack you which you have entered. Okay, so quick recap. What we've done here is we first figured out how to overflow a program. Then we figured out that what we need to know is the exact offset for the return address and ESP. We found that out by sending a huge pattern using pattern_create. Then after figuring out the return offset as well as the value of ESP, we used both of that to create an exploitation case where we overrode the return address with the address which pointed to ESP, and ESP is basically going ahead and pointing to our payload, and hence when the function returns, the EIP points to this return address, which in turn points to the stack where our payload is there, and our payload gets executed. So very simple program which we have exploited. I would go ahead and actually encourage you to download this program. The link is given on the same page, server-memcpy.exe, and see if you can exploit this by yourself. I would urge you to probably use a Windows XP based platform for the initial few exercises so that we are all on the same page when we are doing this demonstration. That's all for this video. I guess it was a very long one. Hope you enjoyed it. Please leave your comments behind. In the next video, we will take a server which is using strcopy as the vulnerable function, and we will look at how to exploit it. Okay, that's all for this video. Bye-bye.